Hello everyone, my name is Jasasvi Sahu. Today I'll be presenting an overview of fault-related faults as a part of my M.Sc coursework in Applied Geology at IIT Roorkee under the guidance of Dr. Sandeep. I'll be talking about an important structural feature in geology, that is fault-related faults, which reveal how the Earth's crust respond to stress and the movement over time. So what are the fault-related faults? Fault-related faults happen when rock layers bend because of the movement along the faults, especially in the areas where the Earth's crust is being squeezed. These faults usually form with thrust and reverse faults and often found in mountainous regions called fold and thrust belts. So why do we need to study fault-related faults? Because first they help us understand the tectonic forces that are shaping the Earth's crust. This fault tells a lot about how stress and movement deep underground affect the surface structures over time. And then, secondly, they're really important natural resource exploration, especially oil, gas, groundwater, because these resources often collect in folded rock layers. Third, fault-related faults are key in earthquake hazard assessment. Since these structures are linked to fault zones, they help geologists to identify the areas at risk for the future seismic activities. Finally, they matter in engineering and infrastructure planning when building rocks, tunnels, or dams in mountainous or tectonically active regions. Understanding these faults help engineers to design safer, more stable structures. Now coming to types of fault-related faults. There are basically three types of fault-related faults: fault-bend fault, fault propagation fault, and detachment fault. First, we have fault-bend fault. This happens when the rock layers move over a bend in a fault. As they slide, the layers bend to match the shape of the fault surface. It's like kind of bending over a step. Then the next one is fault propagation fault. This one forms at the end of a fault that doesn't reach the surface. Instead of breaking through, the force is absorbed by folding the rock layers above it. Then there is detachment fold, which forms above a weak, slippery layer underground, like clay or salt. When compressed, the top layers fold while the bottom layer slides, causing a wave pattern. And finally, the force fold. The fold is directly caused by the fault moment that pushes the rock into a fold shape, even if the layers would not normally fold like on their own. This slide shows three main types of fault related folds. Let's start from the top. First, we have the undeformed state. This is how the rock layers look before any faulting or folding. They are flat and undisturbed. You can see in the figure A, this is the undeformed state. Then detachment fold. It forms when the rock layers above a weak or slippery surface, that is called a detachment, are squeezed. This pressure causes the upper layer to fold, but the core may be filled with soft or mobile material. Then we have the fault bend fold. This happens when rock layers are pushed over a bend in a fault. As the layers move off and over the bend, they get forced into a fold shape, usually forming an arc or what's called an antiformal structure. Here in figure C, you can see that the fault is taking an antiformal structure like shape. And finally, the fault propagation fold. This one forms at the tip of a fault that doesn't break all the through. As the fault pushes upward, the layers above it buckle and fold instead of fracturing. So these folds are closely tied to fault moments and give us clues about how the Earth's crust responds to stress. Okay, now what is force fold? Force fold are the fold that form due to external forces such as displacement along a fault. So the folding is directly caused by a mechanical force such as a fault tip pushing or dragging the layers. Example fault bend fold, fault propagation folds. So force fold are a broad category that includes many fold types caused by the tectonic movement. Now décollement fold. What are décollement fold? Folds that form above a weak horizontal detachment surface or a décollement, often due to compressional buckling. These folds develop above a zone where the movement is decoupled. The weak layer allows the overlying strata to buckle. It is a specific type of fold and it can be considered as a subset of force fold if the buckling is due to the external compression. So, in summary, all decolming folds can be considered as force folds because they result from horizontal compression. But not all the force folds are decolming folds because some like fault bend or fault propagation fold does not involve decolming surface. Now coming to detachment folds. These are also known as decollement folds. They form when the rock layers are compressed above a weak ductile layer such as salt, clay, shale, called a detachment horizon. Instead of breaking, the overlying layers simply bend and fold, forming a structure without any fold breaking through to the surface. So deformation is accommodated by folding, not faulting, at least initially. These folds are typically broad, boxy, or symmetric in shape. You can see in the image that the folding occurs above the red dashed line which marks the detachment fault. Compression is absorbed by folding of the upper layer while the ductile layer flow below. This process is especially important in areas with thick salt or shale deposit and it often plays a role in forming the hydrocarbon traps also. So here you can see the pre-growth strata. Here layers deposited before the folding started. They were originally flat. And here you can see the growth strata. These are the layers deposited during or after the folding. They adjust to the shape of the growth fold and maybe thinner tilt. If the compression continues, a detachment fold, which originally forms without folding, may eventually develop a fold. This transforms it into a fault propagation fold, where the fault pushes upward and folds the overlying layers. These structures commonly occur in fold and thrust belts, foreland basins, with ductile layers like salt or clay or shale, and in regions with thin skin tectonics where only the upper crust is deformed. On the right, we see a real-world example of a detachment fold. The curved layers showing how compression has deformed the rock above a weak layer. Now coming to basic type of detachment fold. Here we have two main types of detachment folds, disharmonic and lift-off. These structures form due to deformation along a weak ductile detachment layer, but the resulting fold geometries differ based on the conditions and materials involved. The first one is disharmonic detachment fold. You can see in the top diagram. This type forms when the folding behavior varies between layers, mainly due to the difference in rock strength or competence. Stronger or more competent rocks resist the folding more than the weaker ones. So, as a result, the folds in the upper layers don't align with those below. You can see that in the diagram you can notice that how the layers appear irregular and mismatched across the stratigraphy. This disharmony gives the fold its name, disharmonic fold. Now the second one is lift up detachment fold. You can see in the lower diagram. This fold forms under extreme compression. The name of the fold comes from how the layers seem to lift off from the detachment surface below. This creates a dome-like or arc-shaped structure as shown in the diagram. Lifter fold typically form above very weak ductile layers like salt or shale that can flow easily under pressure, allowing the upper layers to rise. So, in summary, while both types involve detachment along a weak layer, disharmonic folds show irregular, uncoordinated patterns due to varying rock strength, whereas the lifter folds form under intense compression and result in more symmetrical and egg-shaped structure. So talking about typical environments, the disharmonic detachment folds, which are very chaotic and irregular, are commonly found in areas with alternating strong and weak rock layers. Like these are very common in sedimentary sequence. And the lift-up detachment folds, which are found in very weak ductile rocks such as salt, shale, or evaporites. They are common in foreland fold and thrust. Now moving on to fault bend fold. Let me explain what a fault bend fold is and how it forms. Before that, let me talk about ram flat geometry. Ram flat geometry refers to the stepped shape of a fault surface in a thrust fault system. It contains mainly two parts, flats and rams. Flats, they are the horizontal or nearly horizontal segment of the fault, where the rock layers slide without much deformation. And rams, these are inclined sections of the fault that connects two flat segments. As the rock moves off the ram, they are forced to bend, forming folds. So, when the rock layers move along this kind of geometry, flat to ram and back to flat, they get bent in a predictable way. Then, let's get to know about leading and trailing anticlines. So, in a fault bend fold, the term leading and trailing refers to the position of the folds related to the movement direction over ram. The leading anticline forms in front of the ram in the direction of the rock layers are moving. The trailing anticline forms behind the ram as the rock layer adjusts after bending over it. Similarly, we get leading and trailing synclines. These features are symmetrical around the ram and help us understand how the layers have been deformed during the thrusting. Okay, from the diagram, you can get uh, ideas about the point I just explained. So now, a fault bend fold. A fault bend fold forms when the rock layers are forced to bend as they move over a stepped fault surface, which is usually part of a thrust fault system with alternating ramp and flat segments. The folding occurs due to motion along a chord fault plane, which typically has a ramp flat geometry, meaning it alternates between incline and horizontal segments. As the rock layers move over the surface, they get bent rather than broken. So, the beds remain continuous but they get folded. These folds are angular and predictable, and they commonly create anticlines, upward folds, and synclines. Those are called downward folds above the fold rams. So, you can see in the diagram, the foot wall remains relatively undeformed, while the hanging wall forms the fold bend folds as it moves over the ram. The leading and trailing anticlines and synclines are labeled to show how these folds appear before and after the ram segment. This type of folding is important in structural geology, especially in understanding mountain building and hydrocarbon traps. Now, fault bend fold mechanism. This slide shows how the fault bend folds develop step by step as the hanging wall sheet moves over a ram in a thrust fault system. So, initially, the rock layers were flat and undeformed, as you can see in the figure A. As the thrusting begins, the hanging wall starts to move up above the ram. This causes flexing of the beds into smaller kink-like folds. These are the early stages of deformation, early signs. You can see in the figure B. Now coming to the third step, with continued movement, these folds develop into clear ram fold with a back limb and forelimb. The forelimb lies above the ram and the back limb bends behind it. You can see in the figure C. Now coming to the next step, the fold grows as more material is pushed over the ram. You can see the horizontal layers being preserved on the forelimb while the back limb accommodates most of the bending. Finally, the anticline continues to grow in height and width as more beds enter the fold. The structure becomes larger and the kink-like zones widen, showing how the deformation evolves through time. This sequence illustrates how motion over a ram creates predictable folding patterns. Those are crucial for interpreting subsurface structure in geology. So talking about common settings of fault painful, these are commonly found in fold and thrust belts like Himalayas, Andes, Rockies, and regions with thick sedimentary sequences under compression. Now let's talk about fault propagation fold. This type of fold forms when a thrust or reverse fold pushes the rock layers upward, but the fold tip hasn't yet broken through the surface. So instead of fracturing, the overlying rocks bend into a fold. This is why it's called a fold propagation fold. The result is an asymmetric fold where the forelimb is stiff and the back limb is gentler. The fold is active at a depth, but it has not got through all the layers ever. So the deformation appears as folding at the surface. As the fold continues to move, the fold grows larger over time. These folds often develop into anticline-syncline pairs, as you can see in the image on the right side. This photo is a great example from Broadhaven in Wales, showing the curved layers bent by the fault moment underneath. Now coming to mechanism, this slide explains how fault propagation fold evolve over time. First, the hanging wall folds as it's pushed by the underlying fault movement. The fault and the fold form at the same time, so their development is synchronized. As the fault propagates upward, an overturned anticline appears above the fault tip on the hanging wall. On the opposite side, the foot wall, an overturned syncline may form just beyond the fault tip. Importantly, the foot wall generally remains undeformed. All the folding happens in the hanging wall. So looking at the diagram in figure B, you can see how the back limb and forelimb starts growing. In figure C and D, the thrusting continues. The fold becomes more asymmetric with a steep forelimb and a gentle back limb. By figure E, the forelimb becomes passive while the deformation continues in the back limb. This shows the progressive nature of fault propagation folding driven by continued movement along an underlying fault. Let's talk about kinematic model of fault propagation folds. This slide helps us understand how fault propagation folds evolve over time through kinematic modeling. On the left, the schematic diagram shows the progressive development of a fault propagation fold. The green dashed line represents the active fault surface. As the fault propagates upward, the overlying layers bend instead of breaking, forming the fold. The distance between the fault neck and the Y handle represents the amount of fault slip or the displacement along the fault. Also, the fault tip and the bifurcation point lie on the same stratigraphic horizon. That means they follow a specific bed or marker layer. Now, looking at the photo on the right side, This is an actual field sample from the northern foreland basin of the Alps in South Germany. You can see how the fault, which are marked by the white arrows, causes bending of the overlying beds, forming a classic fault propagation fold structure. This is a great real-world confirmation of the theoretical model on the left. Overall, this slide connects the conceptual model with a real geological structure, reinforcing how the theory is observed in nature. Now, let's talk about kink band. This slide explains the concept of kink bands, which are important structures in compressional tectonics. A kink band represents piecewise linear deformation, meaning the layers don't bend smoothly like a curve. Instead, they bend sharply at distinct hinge zones. These hinge zones act like mechanical hinges, creating segments of rock that stay straight between the bends. Kink bands are most commonly observed in fault bend folds, especially in thrust belt regions, where the compressive force is dominant. We use kink band models like the one shown up right to the geometrically described sharp angular folds that form when the rock layers are forced over ramps and flats in a thrust fold system. So essentially, kink bands gives us a simplified but powerful way to model the sharp folding seen in many real-world geological settings. Here in the diagram, you can see a kink band model in cross section. You can see that the rock layers are flat and parallel until they abruptly change direction at the two kink zones. These zones here and here are the hinge lines where the deformation is concentrated. Inside the kink band, the layers are inclined but still maintain their thickness. That means there is no internal deformation of the rock units, just there is a change in the orientation. The red lines indicate the geometry used to model the angles and the position of the layers, making it easier to understand how the fold develop as the layers are pushed over a fault ramp. This model is very useful because it simplifies the complex folding into a predictable pattern, which helps us in structural interpretation and kinematic analysis. Now coming to tri-shear model. This is another model which is a kinematic model used to describe how rock layers deform ahead of a propagating fault tip, particularly in fault propagation folds. Rather than all the deformation happening straightly along the fault plane, here the strain is distributed within a triangular zone. It is called the tri-shear zone. In the diagram which is shown in yellow, this zone widens away from the fault tip and represents an area of distributed shear. You can see how the rock layers get progressively more wrapped and asymmetric as you move through the zone. The strain is highest near the tip of the fault and decreases outward, which lead to features like rotated limbs and layers with non-uniform thickness. So, this model helps us explain the asymmetric fold geometries that we often observe in the field but cannot model with simple methods like kink bands. So, now if we compare the models, then in kink band model, the type of deformation is piecewise linear, while in fault bend fold, it is a sharp bend over ramps, and in tri-shear, it is gradual and distributed. And if we talk about the strain distribution, in kink band model, it is localized at hinges, but in fault bend fold, it is localized, and in tri-shear, it's spread across the tri-shear zone. Talking about the fold symmetry, in kink band model it's often symmetric, and in fault bend fold it's sharp limbs, and in tri-shear it is asymmetric folds. And if we talk about the layer thickness, this is uniform in kingpin folds and also uniform in the fold pin folds, but in tri-shear it varies across the fold. Now, this slide further represents the tri-shear model, which explains the distributed deformation near a fold tip. It is an alternative to the kingpin model when explaining more complex asymmetric fold structures. So here in the left diagram, this is the velocity model. On the left, we can see the fault plane separating the hanging wall from the foot wall, which is assumed to be fixed. Above the fault tip, the tri-shear zone where the deformation occurs. The arrows indicate velocity vectors of a material particles in the hanging wall as they move relative to the foot wall. Now notice the apical angle which defines the shape of the tri-shear zone and the direction of the velocity change across it. Now in the right side, the diagram shows the actual structural expression of this model. You can see asymmetric folds forming due to the distributed shear. These are not sharp like in kingpin models, but these are more gradual. This explains features like foot wall inclines, forelimb thinning, and stepping downward folds. So, overall, the tri-shear model helps us to understand how gradual, non-uniform deformation near the fold tip leads to complex fold geometries, especially in extensional and compressional tectonic setting. Let's talk about drag folds. As you can see in the diagram, in the accompanying image, the drag folds are essentially small-scale curved folds that form right next to folds. Think of it this way. Imagine two blocks of rock moving past each other along a fault line. As they slide, the friction between them causes the layer of rock immediately adjacent to the fault to bend and drop. This bending creates the characteristic curved folds. Notice how these folds can be either concave or convex, that is curving inward or outward. And the direction of this curvature actually tells us something really important, that is the sense of movement along the fold. By observing the shape of the drag fold, we can often determine whether the fold is normal fold, like where the hanging wall moves down relative to the foot wall, or a reverse fold, where the hanging wall moves up. So, in essence, drag folds are like little telltale signs right next to a fault, which gives us valuable clues about how the rocks have moved and deformed. They are often asymmetric, means one side of the fold is steeper than the other, further reflecting the direction of the fault movement. You can clearly see this curvature in the layer in this image. Talking about the next one, the diagram on this slide illustrates a drape fold, also sometimes called a forced fold. Here is uh, you can see that this diagram illustrating a drape fold. Notice how the layers of the rock are bending and draping over a pre-existing uplifted structure. The key thing to understand here is, unlike the drag fold we saw earlier, these folds are not primarily caused by horizontal squeezing or compression. Instead, they form because of the vertical movement of something underneath the sedimentary layers. In this diagram, the stippled area represents that underlying structure. It could be a fault block that has moved upwards, a rising salt dome pushing through the layers, or an anticlinal oblique where deeper rocks are being pushed up. As this basement structure moves vertically, the overlying softer sedimentary rocks are forced to bend and accommodate the change in the shape below. The result in a gentle, broad fold that essentially drapes over the uplifted feature. You can see in the diagram how the layers thin out or sag slightly on the flanks. and thicken over the crest. This is a characteristic feature of a drip fold. So remember, the folding here is not due to a horizontal push, but rather a vertical forcing from below, causing the layers above to bend and drip. So, to wrap things up, this slide highlights the key importance of understanding fault-related folds. Firstly, the fault-related folds acts as a crucial link between brittle fracturing and ductile folding within the Earth's crust. This means that the rigid fracturing of rocks along the faults often lead to more plastic bending and wrapping of adjacent layers that demonstrate a spectrum of rock deformation. Secondly, their formation is directly controlled by the geometry and movement of faults, particularly in areas where the tectonic plates are colliding and squeezing together. That is the compressional tectonic setting. The shape and orientation of the fault, as well as the direction and amount of movement along it, dictate the type and style of folding we observe in real life. Thirdly, studying these structures is essentially important for a wide range of geological applications. This includes understanding how the mountains are built over millions of years, assessing potential seismic hazards by identifying active fault zones, and even guiding resource exploration for things like oil and gas that can be trapped in the folded structures. Ultimately, the study of fault-related folding provides a powerful illustration of how the rock layers respond to the immense and complex force at play within the Earth's crust. These processes shape the dynamic landscapes we see around us, from towering mountain ranges to subtle bends in rocks. These are the references I have taken for my PPT, and thank you so much.